All right, this is section 9.3. We talk about rates of change and derivatives. So first off, let's talk about a lot of different definitions that are equivalent. These are basically the same thing, just in different words. M, slope, average rate of change, velocity, derivative, marginal revenue, instantaneous rate of change. All these mean the same thing. So let's take the traditional way of talking about slope. So if you got 2 points, x1, y1, x2, y2, your slope is just y2 minus y1 over x2 minus x1, the difference of the y's over the difference of the x's. We all know that. We can also talk about some point A and f of A and some point B, f of B. And so in the same vein, we got the f of B minus f of A over B minus A. And so you can see 2 points here, A, f of A, B, f of B. And you can see a line here. This is technically called a secant line, a line that touches a function in two spots, like this. What you can do is you can find the rate of change, or the slope, of this line, and that will approximate what you're trying to eventually find, which is the rate of change at one individual point. But we'll get into that a little bit later. So then you can also talk about x, f of x, and x plus h, f of x plus h. H is going to be a very small number that gets infinitesimally small, almost to the point of 0. And when we analyze this, we're going to be able to find a technique or an idea called the derivative. But for now, M is f of x plus h minus f of x over x plus h minus x. And x plus h minus x is just h. So this thing becomes the difference of the f of x plus h minus f of x, all divided by h. Alright, so let's talk about example 1 here. It says suppose a company has a total cost function given here. It says find the average rate of change of the total cost for the second 100 units produced, meaning from 100 to 200 units produced. Well, you have to find out the cost when you produce 100 and find the cost when you produce 200. And when you do that, now you've got two individual points instead of just two x values. You now have an x and a y, an x and a y. And now you can find the slope. And we find that it's $28, meaning the change in dollar amount per unit, when we're talking about making between 100 to 200 units, it averages about $28 per unit, whatever item they're making. Example 2 talks about the percentage of elderly men and women in the workforce, and it gives you percentages. The one on the left is men, and the one on the right is women for each of these years, going from 1970 to 2040. And these are percentages. All right, so then they ask you to find the average rate of change of the percent for men, and then eventually also for women. So for men, you've got 1970, 26.8, and you got 2040, 17.3. So you got your 2 points, you take your slope, and you get your answer. And that's the rate of change of the percentage of elderly men in the workforce per year. So it's actually decreasing for each successive year. And here's the way you would write that. Now the same thing for women. You can come up with the two numbers here. 1970, 9.7, 2040, 10.1. And so you do the slope formula again. And notice this one actually has an increase per year. So it means the percentage of elderly women in the workforce as the years go by over this 70-year span is actually increasing per year. Instantaneous rates of change or velocity. Another common rate of change is velocity. For instance, if we travel 200 miles in our car over a 4-hour period, we know that we average 50 miles per hour. However, during that trip, there may be times when we are traveling on the interstate at a faster than 50 miles per hour, and times when we're stopped at a traffic light. Thus, for the trip, we have not only an average velocity, but we also have instantaneous velocity, or instantaneous speeds as displayed on the speedometer. let's see how average velocity can lead us to instantaneous velocity. Suppose a ball is thrown straight upward at 64 feet per second from a spot 96 feet above the ground. The equation that describes the height, y, of the ball after x seconds is given here. So notice that at time 0, it's 96 feet off the ground. And at time 2, it's a lot higher. And close to here at time 5, it's almost almost hit the ground. All right, so this is your function here. And it shows the function from 0 to 5, meaning 0 seconds up to 5 seconds. And the y-coordinate is your height of the ball at that time. So if you want to look at some velocities, you can look at 1 second, it's 144. At 1.01, it's 144.3184, and so on, all the way down here. So you've got your 5 different points here. So we can do the average velocity. Starting with from 1 to 2, we get 16. And then from 1 to 1.5, we get 24. And then 1 to 1.1, we get 30.4. And 1 to 1.01, we get 31.84. And so what we're trying to do is find the velocity at time 1, when x equals 1. So we change that second point to a number that's closer and closer to 1, and the closer and closer we get to 1, the more accurate our answer is. And so the instantaneous velocity at 1 is closer to 31.84 feet per second than with 1.1 versus 1.01, which is 30.4. So 31.84 is more accurate. All right. So if we represent the change in time, which we were talking about earlier, here we had initially a change in time of 1 second, a half a second, 1/10 of a second, and 1/100th of a second. If we represent the change in time by h, then the average velocity from x equals 1 to x equals 1 plus h approaches that instantaneous velocity at x equals 1 as h approaches 0. So we're going to use the idea of a limit here to help us define this instantaneous velocity. So we got the same question here. We're trying to find the average velocity from 1 to 1 plus h. So first thing you should do is you should write out the function with blank parentheses everywhere you see an x. Then when you go to find these two different values in the numerator for your slope, they're a lot easier to figure out. You just plug a 1 in for the blank parentheses, and then you plug a 1 plus h everywhere you see a blank parentheses. Well, the first one gives you 144. We already knew that. The second one, when you multiply this out, you get 96, 64, 64h. Here, you have to be a little more careful here. This is 1 plus h times 1 plus h. And so that gives you a 1 times 1. It gives you an h times h, but it also gives you a 1h and another 1h, which adds up to 2h. If you're going to make a mistake, the most common mistake is to forget that middle term. Now you multiply this by negative 16 and you get this. And now notice it simplifies down to some h squared, some h's, and some constants. So now here's your f of x plus h. Here's your f of x over x minus x plus h minus x, where x is 1. And so when you simplify this, your 144's cancel out, your 1's cancel out, you just get h. And when you divide h into each one, you get 16h and 32. And so that's your average velocity. Now if you were to take the limit as h goes to 0, that would mean this term goes away, and your answer is really 32 feet per second, which is actually the correct answer to the question. So note, average velocity is found over a time interval. Instantaneous velocity, or velocity, can be found at any time x, as follows. Suppose an object is moving in a straight line as a position y at time x given by the function, then the velocity function is simply the limit that we just looked at in the last problem. Instantaneous rate of change of any function, commonly called rate of change, can be found in the same way we find velocity. The function that gives this instantaneous rate of change is called the derivative. This is a very important concept in this chapter. So if f is a function, then the derivative of f is denoted by f prime of x, and you find the limit of this slope idea. So if it exists, we say that f is differentiable at that function. Now how do you find this derivative? Well, there's two steps involved. First step is you have to find what f of x plus h is. So I write the f of blank idea, blank wherever you see an x, and I plug in x plus h everywhere I see that blank parentheses, and I multiply it out. Now you have to be careful here, especially because x plus h squared ends up being x squared, 2xh, and h squared. You're going to get the x squared, the h squared, and then your middle term is xh and xh, meaning two of them. Distribute that minus 8, and you get this. Alright, so now here's your f of x plus h, which goes right there. It replaces this. Here's the original function itself over h. Now when you drop the brackets or parentheses, you distribute that negative sign here. That changes the sign of each one of those. And now notice your 5 and minus 5 go away, your 20x and minus 20x go away, your 8x squared and minus 8x squared go away. And if you do this properly, you should only have terms at this step that only have an h in them. Now you divide h into each one, and you get this. Now when you finally take the limit, as h goes to 0, you plug in 0 for h, and that last term goes away, and you just get 20 minus 16h. And that is your derivative of the original function 5 plus 20x minus 8x squared. Now there's many ways that we can denote a derivative with f prime of x, y prime, dy dx, d dx of f of x, d sub x of y, d sub x of f of x. The most common ones are f prime of x or y prime or dy dx. These first three are the most common. These last three are rarely used. For the linear function, we define the marginal revenue as the rate of change of the revenue function. If the total revenue function is not linear, which is what we're going to be looking at in this chapter, we define the marginal revenue as the instantaneous rate of change or the derivative of the revenue function. So, marginal revenue is given by MR bar, that's bar over the capital MR, equals R prime, which is revenue with that little tick there indicating it's the derivative of R, and it's just the limit of the this fraction here, by the way, is called the difference quotient. It's an idea that Isaac Newton first thought of when he was coming up with the idea of calculus in 1648. Note that the marginal revenue or derivative of the revenue function can be found using the steps on page 7, which is what we just did, these steps here. These steps can also be combined as they are in example 4. So example 4 says find the marginal revenue for any value of x and then find the marginal revenue at x equals 20. So you take the function and you analyze this difference quotient. So you're going to plug in x plus h everywhere you see an x. And then you're going to take the original function itself and subtract the 2 all over h. Now when you multiply this thing out, you get all of these terms, and you distribute that negative, you get those two terms, and a bunch of them cancel. Like I said, if you do this properly, you should have only terms with an h in them. And divide h into each one, you get this guy here. Now you're ready to do direct substitution, taking the limit as h goes to 0, and you get 100 minus 2x. So this is the derivative for any value of x. Now if you want to do a specific value of x, you just plug in 20 in for x and you get 60. Hence the marginal revenue at x equals 20 is 60 or $60,000 per 1,000 barrels of oil. So that's the rate of change of the revenue as you're producing 20,000 barrels of oil. Tangent to a curve. Just as the average rate of change are connected with slopes, so are instantaneous rates or derivatives. In fact, the slope of the graph of a function at any point is the same as the derivative at that point. Right? The slope of the graph of a function at a point is the same as the derivative at a point. To show this, we define the slope of a curve at a point on a curve as the slope of the line tangent to the curve. So we've got a line that touches only at one point on the circle, And if we want to do the same idea here, we're going to use this line L. Now you can have other lines that only cross it in one spot, but these are not the ones that we really want to think about. We want to think about a line like this where it only touches in one spot, and it's right on the edge of your function there. Now, what Newton did was he said, how do I find the slope of the tangent line here, L? That's our goal. Well, he said pick some other point here, called it Q1, and he used point A as well, and he found the slope of that. Then he moved it to Q2, a little bit closer, and he found the slope of that. And then he did the same thing for Q3, Q4, Q5, and he kept getting closer and closer and closer to A. And what he ended up doing was getting closer and closer to the actual answer, which is the slope of the tangent line that only touches in one spot. Trouble is, if you want to find the slope of any tangent line, you need to have 2 points, not one. Well, he came up with this idea, which is x and x plus h, and f of x and f of x plus h. And that's where he came up with this slope idea, which is the same thing as what we had before, just instead of saying x, it's saying x sub 1. That typically means that they have some specific value for x. And then when we take the limit of this, as h goes to 0, we get our actual answer at that one individual point. And so here's the slope of the tangent line. It looks exactly like our derivative, which it is, and it's our derivative for x equals x sub 1, some x value here. So example 5 is doing that exact thing. So instead of using x plus h and x, we're using 2 plus h and 2, because your x value here is 2. Everything else is done exactly the same way, and you get your answer of 4. Now look at the point 2, 4, and here's your tangent line, and it only touches at that one spot there. And if you looked at that line and analyzed its slope, you'll find out that it has a slope of 4. It's quite steep. Thus, the slope of the tangent to y equals x squared at the point 2, 4 is 4. The statement, the slope of the tangent to the curve at 2, 4 is 4, is frequently simplified to the statement, the slope of the curve at 2, 4 is 4. Knowledge that the slope is a positive number, notice it's positive because the slope is going up from left to right, tells us the function is increasing on that interval. So notice the function is increasing or rising, which means that the point moving along the graph on the function rises as it moves to the right on that interval. If the derivative and the slope is negative, hence something over here, that means the curve is decreasing on the interval, and the point that we're talking about is falling as it moves to the right. Okay, so your slope of the tangent line will tell you if the original function is increasing or decreasing at that point, based on if the slope is positive or negative. Example 6, given y equals f of x equals this function here, find the derivative, then find the slope of the tangent, and then find the equation of the tangent line. So to find the derivative, we have to do the difference quotient with the limit, and we do all that. We already know how to do that, and we get our answer. And now they say find the slope of the tangent line. Well, you use the x value they give you here, which is 1, and you plug that into the function, and you get 8. So now we know the slope of the tangent at the point 116. We know the slope of the tangent to the curve at the point 116 is 8. So now if we want to know the equation of the tangent line, we know that we have the point 2, 4, or excuse me, not that one. We know that we have the point 116, and we have the slope is 8. Right, so we plug in 8 for m and 1 for x1 and 16 for y1, and we're able to find the equation of our line. This is actually the wrong graph. I should not have put that there. So remember, when you're finding the equation of a line, you can use y minus y1, m times x minus x1, where x1, y1 are given, and m is also given. And there's your equation of the line, of the tangent line at the point 116. So what are the different ways of talking about the derivative? All of these are equivalent. Finding the velocity, finding the instantaneous rate of change, finding the marginal revenue, finding the slope of the tangent line. All of those mean exactly the same thing. All right? So example 7 says let f of x equal this, and says use this difference quotient and two values of h to make an estimate of the slope of the tangent. So instead of doing the limit, we're just picking numbers that are closer and closer together, sort of like what we were doing with the secant lines with Q1 and Q2 and Q3. So we choose a very small h that's positive, and we do our difference quotient, and we get -4. And then we do a very small negative number, and we do the same thing, and we get -4. Thus, we can surmise that the derivative at 1 is -4. For B, it says use the following table to estimate g prime of 3. Well, if you want to do g prime of 3, you want to pick something that's very close to 3. So you want to use 2.99 or 3.02. I went and used these 2 points, 3, 10.5, and 2.999, 10.513. Use those two, and I use the slope formula, and I get -13. Notice this is a different question than A is. A has a given function. B is a different one completely. It's a table. So far we've talked about how the derivative is defined, what it represents, and how to find it. However, there are functions for which derivatives do not exist for every value of x. The figure below shows some common cases where the derivative f prime of c does not exist, but f prime exists for all other values of x. These cases occur where there is discontinuity, a corner, or a vertical tangent line. Right? So we're talking about these are places where it's not differentiable because you got a break there, because you got a sharp edge there, because you have a vertical tangent there. And same thing here, vertical tangents. You can't have a vertical tangent or a corner or a break if you want to find the derivative. Right? Now, differentiability implies continuity, means if something is differentiable at a point, then it is continuous at that point. Now notice these last three were all continuous at that point, but they weren't differentiable. So continuity, if something has continuity, does not mean it's differentiable. But if something is differentiable, then it is continuous and does have continuity. Alright, so let's look at the examples here in 9.3 that are similar to your WebAssign questions. The first one, it says, find the average rate of change over the specified interval. Well, to find the average rate of change or slope, you have to find 2 points. And you got to find the y-coordinate for each of these x values of 0 and 5. So this gives you the point 0, -12, and 5, 18. And now you can just do your slope formula, and you get 6. Same idea here, you plug in -3 into the function, you get -6, so there's 1 point, -3, -6, and then plug in 10 and you get 98. So now you've got your difference of the y's over the difference of the x's, and you get your slope formula. Same idea here, they're using 2 and 5 for your x's, and you get 20 and 30 for your y's, so you take the difference of each of those and you get your answer. And same thing here. 3.817 is 1 point, 416 is another point, and you do the slope formula for that one. Find the instantaneous rate of change at x equals 4. So they give us the derivative, 8x, so now we just plug in 4, and that gives us our instantaneous rate of change because the derivative is the same thing as instantaneous rate of change. B says find the slope of the tangent at x equals 4. Well, that's the same process. You plug in 4 into the derivative, and that gives you the slope. All right, and then C, the point on the graph at which x equals 4, that's where you plug 4 into the original function, and you get the y value of 64 there. So that gives you the point 464. Number 9 says use the definition of the derivative and the procedure example box on page 562. That's the steps that you'll find on page 7 in my notes. So you analyze the function for 3x squared minus 2x, and you plug in x plus h here, and you plug in just x there, and you divide it by h. It simplifies down. You take the limit, and you get your derivative. Then it says find the instantaneous rate of change when x equals -1. That's just plugging in -1 into the derivative. Then it says find the slope at x equals -1. Same thing. You plug it into the derivative. Then D says find the point where the graph is at x equals -1. You have to plug that into the original function. 13, they say find the coordinates of P and A. Well, P is 1, 3, and A is 0, 3. It says use those coordinates to find the slope of the tangent line. Here's your tangent line right there. You would expect it to be 0, and when you do the slope formula, you do get 0. Then C says find f prime at 1. F prime of 1 is the slope of this tangent line, and we would expect it to be 0. Then it says find the instantaneous rate of change at P, which is the same thing, and we would expect that also to be 0. 15 says find the derivative using the definition. So we take this equation and we plug in x plus h, and then we just plug in x and we divide it by h and take the limit. And we get down here and we finally get our derivative is 10x plus 6. Now they say find the instantaneous rate of change for any given value. Well, that's the same thing. It's the derivative. And now they say they want you to find for a specific value of f of -2, so you plug in -2 in for x and you get your answer. Then they say find the slope of the tangent. Well, it's the same thing as finding instantaneous rate of change. It's just plugging in -2 into the function and you get the same answer. 25, it shows two different lines with tangents at points A and B. And it says, is f prime of x greater at point A or point B? Well, f prime of x is the slope at that point. So here's a positive slope and here's a negative slope. So if A is positive, you would expect A to be greater because it's positive. Then B says estimate the f prime of x at point B. So you're trying to find the slope at that point. Well, you can pick 2 points here. You can pick a point approximately right there, which is 3, 10, and a point right there, which is 6, 8. And when you take the slope of those 2 points, you're going to get -1/3. If the instantaneous rate of change of f at the point 2, -4 is 5, write the equation of the tangent line. So they give you 1 point, and they give you the slope, and they ask you to find the equation of the tangent line. Well, you just plug those into the equation and solve for y. It says, because the derivative of a function represents both the slope of the tangent line and the instantaneous rate of change of the function, it's possible to use information about one to gain information about the other. So 31a says, over what intervals between A, B, C, and D here is the rate of change of f positive? Well, the rate of change here is positive with A and with B, interval A and interval B. And here from here to here it's positive, well, that's interval D. And what interval is the rate of change negative? Well, negative here, and that's interval C. At what points A through E, capital A through E, is the rate of change of f equal to 0? Well, your tangent line is flat here at A, at C, and at E, and that's the rate of change equaling 0, so A, C, and E are your answers there. 35, they give you the equation x squared plus x, and they give you the point 26, and they ask you to find the slope of the tangent at any point. So you do the derivative difference quotient limit. Do the limit with the difference quotient for that individual function, and when you simplify it down, you get 2x plus 1. Then for part B, it says find the slope of the tangent at the given point, and the given point is 2, 6, so you plug in x equals 2 into your derivative. Then part C says find the equation of the tangent line. Well, we know the slope is 5, and we know the point is 2, 6, so we plug them in, and we get our answer. And here's our graph at the point 2, 6 right there. It only touches in one spot. It has a slope of 5. And that is the y equals 5x minus 4, and here's your original graph of x squared plus x. 39, you're given the cost function is this. They say find the average rate of change between 100 to 300 and 300 to 600 and interpret your results. So in order to find the rate of change or slope, you have to find points. So you plug in each of these x values and get the equivalent y value. There's your 3 points. So the first one says from 100 to 300, so you use these 2 points to find your slope. The second one is from 300 to 600, so use these 2 points to find your slope. And so what's the first one? It's the average cost per printer when 100 to 300 are produced is about $43 per printer. Now what's the average cost when 300 to 600 printers are produced? Well, the average cost is $95.50 per printer. All right, 40. If an object is thrown upward at 64 feet per second from a height of 20 feet, its height is given by this equation. What's the average velocity in the first 2 seconds and the next 2 seconds? And again, same idea, you need to have points here. So you plug in x values of 0, 2, and 4, and you get 20, 84, and 20. And so for the first 2 seconds, from 0 seconds to 2 seconds, you use these 2 points to find your slope. And then from 2 seconds to 4 seconds, you use these 2 points to find your slope. And so it makes sense that when it's thrown up, it's going up at a positive velocity of 32 feet per second. And then after 2 seconds have gone by, now it is falling at a rate of 32 feet per second. So it's actually got a negative velocity. 41, you've got the demand function is this. What is the average rate of change of the demand function when p increases from 1 to 25 and 25 to 100? Again, you need y coordinates here. So from 1 to 25, you use these 2 points and find your slope. From 25 to 100, you use these 2 points and find your slope. Alright, so this one says, what is the function that gives marginal revenue? Well, you have to find the derivative of the revenue function. So you do the limit of the difference quotient for each one. And we know how to do that. And we get our answer is 300 minus 2x. B says, what's the marginal revenue if 50 are sold? Well, you plug in 50 into the marginal revenue. And it means the increase in revenue from selling the 51st unit is $200. 140, plug 140 in, you get 20, and that means the increase in revenue from selling the 141st unit is about $20. And then it asks you for 150, the increase in revenue is 0, meaning you do not get any increase in revenue by selling the 151st unit. Alright, as the number of units sold passes through 150, what happens to the revenue? Well, it changes from increasing to 0, and it will finally change to decreasing. Your revenue will actually decrease if you produce or if you sell more than 150 units. 147, you plug this into your the limit of the difference quotient, simplify it down, you get your answer, and you finally get 4x. And so that's your derivative. It's also the instantaneous rate of change. Now they ask you what's, that's q prime of x equals 4x. And they ask you what's q prime of 50, you just plug in 50 for x and you get 200.